Hello everyone, welcome to my talk about the user interface framework that we created for Cyberpunk 2077. I want to take you to a journey of creating a custom UI framework in Red Engine and show you how complexity and density of that UI in the game was increasing over time and what kind of optimization we used to stay within budget of memory and time. My name is Arkadiusz Antonik. I'm working in game industry over 10 years, mostly in CD Projekt Red. I had the pleasure to work with different areas, expanding my technical knowledge as well as managerial experience. During Cyberpunk 2077 development, I created and I was leading the UI code team. At this moment, I'm focusing on directing technical team for our new AAA game in the Witcher universe. After that short introduction, let's check what we have on the table. As I said, in this talk I want to take you to a journey of creating and using user interface framework, showing you how simple framework can enable creativity explosion, and in the main part of this presentation I will discover together with you what kind of optimization and tricks we had to use to have UI everywhere in the game, keeping the defined budgets. I assume most of you heard about Cyberpunk 2077. However, for those of you who are not familiar with the game, here is a short video showing what is the playground that we will be discussing during the next dozen minutes. Small game for you. Try to find places where you can see UI framework use cases. Usually, game trailers don't have UI, but in this case, we smuggled some elements that are using UI framework. Let's take a look.
Test of a person's true value. Death. Facing, staring it down.
Johnny!
I got you.
Pressure's tanky!
It's neurogenic shock. He's dying.
V, you in there?
My head. So what now?
Now, you find out what it is you need to do.
A thing of beauty, I know.
You've never backed down from anything in your life, even when you maybe should have. You go through Night City knowing a stray bullet could end you while hailing a cab. But that's never stopped you from taking action. You believe you cheated death. It is death that has cheated you. If you gotta kill, kill. If you gotta burn it all to the ground, then let it burn.
Elevate! On the ground, asshole! Don't move!
Out of my house! No!
Will never fade away. What you did to me, I know. So how I find a way, but I think of beauty.
Would you rather live in peace as Mr. Nobody, or go down for all times in a blaze of glory?
Will never fade away. Will never fade away.
Okay, we know what's the game that I will be referring to. It's time to check where that journey began. Let's back in time. We have the year 2016. We finished Witcher 3 Blood and Wine expansion and started working on a new title. You know the quote, Something ends, something begins. We moved the bar higher for ourselves, so we wanted to have much more of everything. And that everything had to be bigger, better, more complex, and more dense. We decided to implement a new version of the Red engine for our next game, for Cyberpunk 2077. As a part of it, we wanted to have our custom user interface framework built into the engine. You can ask, why? And it's a very valid question. Let's dig deeper. Big expectations didn't omit UI area as well. We can define two directions of the expectations. Technical side. The most important part was to integrate each piece into the in-engine environment. Learn from the past that using external third-party software, we didn't have enough power to adjust it and optimize it. We wanted to have a full control over each stage of the software, plus increase efficiency by integrating the whole framework into Red Engine architecture. It is file system, renderer, streaming, editor, and so on and so forth. Having all under control, we wanted to push more having bigger density and complexity of the UI in the game. The second side of the coin is the creative side of these expectations. From the creative side, we wanted to introduce multiple languages possible to display at the same time and convert one to another visually. On top of that, we decided to push the UI into 3D space. At the beginning, it was not fully clear what does it mean, but we knew we wanted to have it. In the end, it's worth mentioning that we wanted to have a space to display pre-rendered videos as an integral part of UI experience. Initial research was not that long. We checked a few existing solutions. However, all of them had some challenges with scalability, and the process of integration with in-engine subsystems was not that smooth as we expected. Many of checked middlewares propose only a part of what we needed, but even if we would like to combine them together, they didn't cover all UI framework requirements. Because we haven't found any suitable solution, or even combination of sub-solutions, we made the decision of creating our internal UI framework. We name it Ink. It's worth to mention it here because you will see this name in a few places later, and it's good to remember it for context. After a few weeks from the decision, we achieve MVP. That means minimum valuable product. It is nothing spectacular, but prove the idea of possibility to connect it with in-engine subsystems and even a few things more. For example, layout building options or proper input propagation. It was June 2017 when we delivered the MVP of UI framework. And it looked like this. The next step was to take that MVP, improve it, and use in the game, in real environment with real challenges. And we did it in less than a half a year. Without any editor, each layout was hard-coded in C++. Framework was fully single-threaded, and it was using debug drawing codes, but it was working. We delivered the first UI in the game in December 2017. And it looked like this.
What's up, Dex? Got some of your sweetness for me?
Sorry, residents only. Got forensics inside.
I live here.
The next step was not that precise. This was a very long process without any strict deadline. Okay, a release date was the final one. But after proving that we are able to deliver and we are on the good path, we started creating final solutions, proper implementation and efficient environment for our user UI designers and artists. During this time, we started creating more and more assets, and we are using UI in many places across the whole game. I think it is worth to see how many assets landed in the final game. I choose only a few statistics, the most interesting in my opinion. And to be fully honest, we didn't expect that big numbers when we started working on UA framework. We knew that scale of that game will be huge. But talking about big numbers in game industry, cannot forget about budgets. In this presentation, I'm focusing only on two, the most important of them, memory and frame time. However, during the development there was one more budget related to I/O operations. It was important in the past because of mechanical hard drives, but currently it's not that important anymore. Of course, after introducing budgets, every system was out of budget. Fitting UI to receive the budget was a never-ending story till the end of the production. But we had a few milestones where things changed, and thanks to that, we were closer and closer to the final numbers. I will describe these gates later in the presentation. Here, you see what was the challenge for us to go from the values we had when we introduced memory budgets to the final expected amount of memory. To monitor every little aspect of memory, we were using our internal debug tools, and one of them you see right now. This one is for tracking memory pools. At the beginning, the second budget was more important for us, because it was not trivial to fit to. There were two questions bothering us: how to decrease execution time and how to spread the execution across many threads. I will show you our approach a few slides later. In August 2018, we revealed the gameplay demo, and we were ready for new challenges, this time connected with budgets. But having budgets is very good. However, from that moment, we have to be more careful and check at least twice what we are doing. Let's check where we consume that memory and time in UI framework and try to answer the very important question: why UI is that heavy? So the first obvious answer is the UI framework is not optimized. Sure, that's true, and the work on improving it is on engineers. However, the second answer is not that obvious. We had too many UI instances around the world, hundreds of independent UI hierarchies, thousands of widgets, dozens of animations, and more. Fixing this part was partially on content teams to optimize usage of UI instances. But from a different perspective, that was the goal, desire of having custom UI framework, to have higher density of UI in the game. So the solution is one and simple. Let's optimize the UI framework in a way that it will be smart and will know what to keep in memory, what to update and draw at the specific moment in the game. To have a better context, let's check two aspects. The first one is complexity, and few examples here. we had to deal with a soup of hundreds, sometimes thousands vector shapes on minimap. Dozens of very dynamic mappings in the world and on the map. Complex UI hierarchies for icons in inventory, not single images, but whole hierarchies. Animated perks based on custom animated post-processes in UI. And many HUD elements cluttering and fragmenting memory. And it's only a small part of the UI in the final game. The second aspect is density. This one came from world. UI was used for features that we didn't expect when we were designing UI framework. Skipping obvious options like displays on weapons, displays in general, computers, vending machines around the world, we had a few really dense and expensive usages that were unique for our game. Billboards or advertisements, localized street signs, global TV system, or even very random but use a big quantity custom solutions like curbs with customized and localized text. To not go too deep, but still give you a perspective, some more statistics. This time, runtime based. To support all of these needs, we had to introduce a few changes and optimizations that I want to show and explain in the next part of this presentation. Before we will start analyzing cases and scenarios, I feel I need to explain a few names, concepts they will be using later in my examples. Here, I want to focus on UI layout, how we design it to have a better management on the whole UI. The smallest, let's say, atomic part in UI is a widget, but this term is widely known and doesn't need explanation. So for us, the small part that we introduce to UI framework is the UI instance. That is independent UI hierarchy instantiated in memory with its all dependencies, all dependent assets and objects like textures, animations, render targets. This UI instance is spawned from widget library item. So next, widget library item. It is a single UI hierarchy, for us a template, that can be spawned, instantiated in runtime and become a UI instance. This widget library item exists in widget library asset. It means that from one library item we could spawn many UI instances that at the beginning look exactly the same, but later, depends on the game conditions, could change their properties totally independently. And the last term is widget library asset. That is asset or file that contains a list, a library of widget library item and all references to dependent assets. So simply, it is a file that contains any number of UI templates plus information about all dependencies to other assets in the engine. Having this long part behind, we can finally start talking about optimizations. We will touch 6 of them. The first one, we need to group UI instances to have a better control. The second one, we need to reduce UI updates to reduce frame time. Third one, we need to reduce UI animation time, the same reason as before. The fourth one, we need to apply UI instance scaling to skip not visible UI in 3D space. Fifth one, we need to introduce deferred update and draw to better use waiting time on threads. And finally, sixth one, we need to introduce eluded mechanism for UI in 3D world to prevent memory fragmentation. The first one, and in my opinion the most important change and optimization at the same time, was grouping UI instances based on UI layers. And here, a quick explanation. Please don't treat this as a layer from common 2D graphics software. It has some similarity, but the most important thing is that UI layer is an independent logical object containing many UI hierarchies, dependent or independent from each other. This object is grouping UI instances and apply on them some rules that are the same for that kind of group of UI instances. Each layer consists of a few main objects that are managing UI each frame. Event broker for queuing and broadcasting events. Spawning processor managing all spawn requests. Controller processor is managing game-related logic. And animation processor is sampling and evaluating animations. More about them later. Additionally, each layer could decide about resources based on the layer specification. You can imagine that resource handling for full-screen UI is different than for UI in world. Finally, in the game, we had 12 different UI layers, separated because we had to handle some specific aspects differently for each of these layers. Mostly, it was related to optimization rules and tricks. We were able to analyze each aspect of each layer in the game using our internal debug tools. Here, you see layer visibility based on the game state and animation for each layer at the specific moment. However, you can ask, Arek, but what? Where is the benefit of UI optimization? So, here it is. It is because of the fundamental design assumptions for the UI layer that you see right now. Based on these design principles, we were able to parallelize UI as much as possible, to be able to shorten the execution time using only a few sync points. Using our internal job system, we were able to schedule, plan a chain of execution, and then execute all necessary logic on as many threads as possible. Let's take a look. This is our internal real-time frame profiler. We can check here how the last frame looked in terms of code execution. In our case, we want to focus on blocks colorized on the aqua color, a very light blue. These are showing where UI code was executed. Our starting point is of course input calculation and propagation. This step is short. Having one cursor in the game plus a smart hit test algorithm, there was no need for parallel execution. Then, we want to start in parallel the whole logic related to each layer management. Each layer can be executed independently, but even in the scope of one layer, we can parallelize specific parts, like controllers or animations. You can ask why not earlier in the frame? Because we need to have a camera position known and some calculation related to world management itself. In this phase, we know how many UI instances we have in each layer. Animations are applied, controller change values inside widgets, and we can arrange all UI instances independently. Finally, we can draw all these UI instances as quick as possible, but there is one caveat. They can be drawn independently only if they are not sharing the same render target. More about this later. We did it. We can decrease execution time significantly based only on the parallel execution. However, each layer applied their custom rules and solutions because we knew how specific widgets or UI instances behave and what kind of boundaries we have for them. There's no more soup of thousands of widgets. We exactly knew what is where and why. Finishing this part, quick takeaway about multi-threading UI framework. To achieve it, we have to first extract all independent calculations and make them asynchronous. Second, use separate render targets to draw UI asynchronously. Third, cache everything what is possible. And fourth, start UI update process in a frame as soon as possible. The most important change is behind. We group and parallelize execution. So, what next? It's time for reducing time. We came up with the idea of two modes of execution, active and passive. That distinction was widely used in the whole UI framework. UI layer and all sub-objects could be executed in one of these two modes. And because each layer is different, each of them could define their own rules deciding which UI instance is passive or active. That split was especially important for controllers attached to UI instances. We named them game controllers. Game controller is a bridge between game system and UI framework. It's spawned together with UI instance, and we can say it owns the instance, having full control over all widgets in that hierarchy. It can manipulate values, play animations, spawn some sub-instances, or remove widgets, all based on information gathered from game systems. What's important? It could be tickable, passively or actively. On the opposite side, we defined objects called logic controllers. These were fully focused on operations related to UI framework. Logic controller could be added only to the widget, and the widget owns logic controller. Specific logic controller could manage the owner widget and all widgets in the owner's hierarchy. In contradictory to game controller, logic controller was fully based on events, without possibility to be ticked or even controlled centrally. In this place, it's worth to mention briefly one of these four main objects in the UI layer, controller processor. It was designed and implemented to spread the whole game-related logic across all available threads. And before that, to be able to check multiple conditions, to check which mode should be executed for each controller inside a specific UI layer. This object was also responsible of gathering all necessary game systems and passing that game context to game controllers. This approach gave us a relatively safe environment for parallel execution. The next object that is continuing the direction of having passive and active modes is the spawning processor. We implemented it in a way that is giving us the possibility to prioritize spawning for crucial and visible objects over not visible objects that were queued and spawned with smaller frequency in the passive mode. The crucial assumption that we had to force for the whole UI was to not waiting for spawning. The default spawning process returns token, not the new UI instance. Each place in UI framework had to deal with this delay properly. Requested UI could be spawned next frame or a few frames later, depends on the I/O availability. It was pretty complex mechanism that had to solve many edge cases to support I/O operations for mechanical hard drives. Additional feature was a pooling system that allowed us to reuse memory that was already allocated if the UI widget library item was the same. useful for lists, grids, or mappings. As long as we could spawn instances in parallel, we had to maintain the order of adding them into the parent hierarchy. This process was sequential, but it was very fast. Finishing this part, we can summarize our separation between logic based on tick from logic based on events. We prove that event-based logic is relevant lightweight, and it must keep a strict control over all tick-based logic. Next, let's try to disable tick always if it's possible. And at the end, avoid data pooling mechanism on the big scale. We covered two main objects, game controller processor and spawning processor. But if you remember, there was one more main object. It was animation processor. And this one needs our special attention because it was challenging. Animation is a crucial feature for user interface. If you remember, we could have hundreds of animations playing at the same time. Each animation is different. They could be simple, but they could be very, very complex, like animations in briefings. One of these briefings I'm presenting you right now. Briefing were the most complex and difficult use cases for this system. We had hundreds of tracks, thousands of value interpolators. We need to synchronize UI animation with video and audio. Briefings were not pre-rendered because they contain localized text. Text was animated as well. And the whole layout had to be very flexible to support different text length. Some briefings were interactive and the player could choose a dialogue option which can completely change the animation flow. The mechanism was built to easily mark possible seams and use these markers to pause, rewind, jump over some sections and play other parts almost seamlessly. To be flexible and reduce memory, we introduce very strict separation between animation objects. We introduced animation definition, an object that contains animation interpolators and events placed on the timeline in very specific order. Order and properties don't change in runtime. Going further, we have a next object type, animation interpolator. It's an object that contains information how to interpolate specific animated property. For example, position, rotation, color, text, effect, or even video. Last but not least is the main object used for animation updates, animation instance. It refers to the animation definition and stores current value of interpolators while playing animation timeline based on delivered playback options. Only this object will change in runtime. As I previously defined two modes, they are applicable for animation as well. For both modes, we need to increment time, and this is obvious. But then, we are evaluating animation and changing values only when player can see the animated UI. Evaluation can be done in parallel because this process only prepares the final value. Applying these values were more difficult because we had to ensure that values are not depending from each other. We grouped dependent values in buckets and inside each bucket we apply them in sequence. If UI is not visible, we need to only secure relevant events placed on timeline because other game logic could depend on them. And once again, quick takeaway about optimization for UI animation. So we can keep only a single animation template in memory and use lightwave animation metadata for each instance. At the end, we can evaluate, calculate, and apply animation values only if effect is visible for the player. For invisible animation, we need to only preserve correct time. Until now, I was talking about UI mostly in 2D space. Let's put the bar higher and go to 3D space. But you can ask why we need to bother ourselves about UI optimization for 3D. Let's face it. It is April 2019. There is a decision that all advertisements across the whole night city will be built using UI framework. Advertisements. This is the main reason why. New challenge, new stuff for the UI budget. To encapsulate the challenge, we introduce a new layer only for this purpose, to have full control over each instant and each operation. You can imagine that walking or driving around the city, looking around, will create a mess of advertisements visible from everywhere. We'll fix it soon. What was the reason for using UI framework here? Generally, to reduce amount of memory needed for each texture, for each possible advertisement format, and additionally be able to make these adverts more dynamic using UI animations. Later during production, we realized that the decision about using UI framework was a very good decision, because we were able to apply, for example, censorship very quickly, or randomize advertisements, creating bigger variety of surrounding environment. Interesting detail here. Randomization broke lighting, because our lighting artists were not able to put proper lights. There was not a proper light if advert could be different every game session. Because of that, we introduced mechanism to mark the main color theme of each advertisement. And we're passing that information to local light to tweak the visual result. One of the most important reasons behind the decision of using UI framework was to minimize texture usage and have more option for dynamic adverts. Having a single texture atlas, we are able to produce a few totally different layouts of the same advertisement in runtime. Additionally, having animation system for UI in place, we can very easily animate all these advertisements. Going forward, having very flexible system of post-processes for widget or for the whole hierarchy, we're able to deliver all kinds of glitches and additional effects. One of use cases for this was a censorship that we needed to apply for some regions. To break the monotony of this presentation, let's play the game. How many adverts using UI framework you can spot on this screenshot? We see 18 adverts created and rendered using UI framework. But this is not the heaviest use case of using this. Please watch this video carefully. There you will see many bounding boxes with different colors. This was our debug mechanism to be sure how many instances we have in view. Blue boxes. How many occluded instances we have. Red boxes. How many dynamic instances. Green boxes. And how many street signs. Orange boxes. To achieve required density in the world, we had to implement various different mechanisms. Some of them are widely known as common optimizations for 3D graphics, like distance check and applying LODs based on it. Frustum culling with movement prediction to avoid popping when advertisements were not fully loaded, and avoid unloading them as soon as possible when they went out of the view. We call it inertia mechanism. Software implementation of occlusion culling gave us possibility to reduce amount of visible advertisements. Big win for us was implementation of screen coverage that was used to determine the render target resolution of the UI instance, that we could better manage memory consumption. For dynamic UI objects like UI in the car, computers, elevator panels, from far distance we switched them totally to static textures. The last optimization was done for in-car mode. When player was driving very fast, then we delay or even skip some calculations for UI instances that passed by. Quick takeaway about view optimization. To achieve it, we had to use optimization pipeline as for normal 3D geometry. Use passive mode if UI instance is not visible. And adjust render quality of UI instances to get their screen coverage. We covered all challenges related to 3D UI. Now we can focus on utilizing threads in a better way. We achieve it applying deferred update and deferred draw for UI instances. Some parts of UI were really heavy in terms of logic. For example, the global TV system that was fully based on UI framework. Having 5 channels broadcasting all the time and being visible possibly in any place in the world require updating and redrawing it every frame. Fast exploration in Night City could cause a lot of troubles because we had many UI instances waiting for calculations a few frames later being out of the player first room. Additionally, we have many icons which are templatized and we have to draw them in a proper hierarchy with proper color, attributes and effects to have the final icon. Having all these things waiting for execution time affecting invisible hitches. But not everything had to be ready and visible immediately. To deal with these new challenges, we introduced a new UI layer, call it off-screen layer. It was in July 2019. The idea behind this layer was to mix the approach of in-world and full-screen layer. The crucial part of this layer was to have a mechanism known as fire and forget. Any UI part could queue some work for off-screen layer, giving a pair of objects, widget library resource as a source, and render target as a target. The whole process of spawning, updating and drawing was fully deferred and not blocking frame. It was using waiting time on threads to do the keyword work. As we introduced the concept of not immediate results in UI, in this case, all places in UI framework were able to use this layer to defer some work if the result was not necessary for a specific moment in time. To visualize it better, I choose the global TV pipeline as an example. Global TV had 5 channels broadcasting all the time. All of them work the same, so we can focus right now only on a single one. The TV scheduler was implemented in a Quest, and from there we received all controlling information. The first one was informing us about the channel template resource. It was a base UI hierarchy needed to spawn and draw. When this part was done, scheduler sent information about pre-rendered video and timestamp for it. It had to be streamed and rendered into the template. And finally, scheduler sent to TV channel information about specific TV channel overlay and news text that had to be localized and then draw on top of the video. All these steps use one render target during the whole process. Each TV layer had independent render target. Here you can see what is the final result of the global TV.
Welcome to the N54 News World Report. I'm Jillian Jordan. Scientists from Biodyne Systems have announced a breakthrough in the fight against multiple sclerosis. MS is one of the few diseases that cannot be cured by replacing the affected tissue with implant technology.
As always, quick takeaway. This time about off-screen layer. Thanks to it, we were able to cache and reuse as much UI as we could. We used frame time only when UI was visible. In other cases, we could defer calculations. We could use fire and forget mechanism because we use independent render targets. We are closer and closer to the end. Right now, we need to focus on one more thing. It is hierarchical level of details for UI in 3D space. We had more and more different UI types for 3D space. And in September 2019, we decided that we need to separate street signs from advertisement layer to have a better control over quality. The street sign layer assumptions were simple. They had to behave similar to advertisements, but with proper localized text and better quality to be able to read it. However, they don't need to be readable or even accurate from the larger distance, what is contradictory to advertisements. Street signs were assembled in runtime based on information from world about their locations. The whole dynamism of advertisements and street sign results in very quick render target fragmentations. And because of that, we introduced Render Target Manager. It was our solution for render target fragmentation. We could use different techniques for drawing UI to specific LODs and preserve part of memory for specific LOD level. From that moment, we never use a raw render target. It was wrapped in a structure which defines the space where UI should be drawn. We treat render targets as texture atlases, split it to smaller chunks, and when UI layer requests a target to draw, then with this request must go a specification about the render target size and orientation. Based on this internal mechanism, could find the best suitable place that is not used and give it to the UI layer as a new render target. Special case was implemented for icons because they don't change that dynamically when we play, and they don't have LODs. At the end, I want to mention that we also separated effects because post-processes use a ping-pong mechanism, behave differently, and HLOD mechanism doesn't fit very well, creating even bigger fragmentation. Here you see two different approaches. On the left is the render target based off eluded mechanism. You can see the same advert but with different sizes. It is like this because when the LOD level change, we never clear the space to not waste time. That space is cleared when it is assigned to a new advertisement. On the right side, you see the render target for icons. They can be drawn sequentially because they are not changing that quickly and have very strict rules about size. They can be multiplied of a given size, so it's easier to avoid memory fragmentation. Here we are. Almost the last takeaway, this time about render target. UI in Word can be very often downscaled without visible quality reduction. And to be sure about UI quality, we can use screen coverage as a factor. The last, we will achieve a better result drawing the whole hierarchy to smaller render target instead of downscaled render target itself. The last optimization is done. We introduced 6 major optimizations. It means we achieve a great success. But why UI is still taking that long? Because there is a bunch of smaller but very important optimizations that have to be done, and we introduce them to the final game. For example, hierarchy caching to not redraw it every frame, data optimizer to reduce cost of recalculation static regex, or remove from memory all glyphs that are never used in any text in the game. We move to data-driven approach for some data-heavy UI instances. Improve animations even more that I show today, especially in terms of text optimizations, animations, and all text recalculation for different languages, including dynamic parameters, text reordering, or different metric systems, and dynamic markup language for images, input icons, or mother tongue feature. Last but not least is the whole complex mechanism for 3D interaction in UI, when that UI is displayed on complex meshes. All of these challenges are fascinating and solutions are not trivial, but they have to be discovered in another time. It is December 2020. The game is finally released. To summarize our journey, I would like to leave with you these 3 main points. Deadlines and budgets are your friends, because they keeping our creativity in boundaries, giving enough freedom to come up with something amazing, and giving real restrictions to push us stop dreaming forever and forge ideas into the real product. Code decoupling and parallel execution give us much more space for additional features and encapsulating specific parts to match them better in these areas. And last but not least, to be able to achieve amazing things, you need to have amazing people around you that are sharing the same passion for making games. Saying that, I would like to say thank you to all my colleagues who are working on UI framework and the whole UI in the Cyberpunk 2077. It was a pleasure for me to be able to meet with them, listen to crazy ideas, and see how they are becoming real features in the game. Thank you very much for your time.